left off in the last session, that was we talked about the properties, some properties of congruences. First of all, if you remember what congruences are, what it means for a number to be congruent to another number, um, then based on that, we talked about some properties, 5 properties to be exact. All right, and then we went on to prove this specific property. And we talked about the proofs of the first 3 properties as well, the basic properties of congruences. Then we went on to prove the property regarding the product of congruences. And you guys were supposed to think about the proof for this property, where it says that if A is congruent to B, if some integer A is congruent to some integer B mod a positive integer M, and some integer C is congruent to D, some integer D mod M, in that case, the summation of the left-hand side, A plus C, is congruent to the summation of the right-hand side, B plus D mod M. That is what you were supposed to think about, how to prove this. Anybody has any idea or clue how we could possibly prove this? All right, first of all, tell me, what does it mean to say that A is congruent to B mod M? What does it mean to say that A is congruent to B mod M?
A minus B is divisible by M.
Exactly. And what about C is congruent to D mod M? C
C
minus
minus
B
B.
is divisible by M. That's correct. Now, in the same way, here, if we had to prove this, then first of all, we have to talk about what it means, right? So what does it mean? A plus C minus B minus D is divisible by M, correct?
Yes, miss.
Excuse me. This statement is basically saying that M divides A plus C minus B minus D. Yeah, that's what it's saying. Yeah, this statement
Yes,
is,
miss.
yeah, and this is what we have to prove, that M does in fact divide these. What do we have in the hypothesis? What is the hypothesis? We are allowed to assume that A minus B is divisible by M, C minus D is divisible by M. That is, we are allowed to assume that M divides A minus B, A minus B, and M divides, what was it? C minus D, right? Yeah, C minus D. We're allowed to assume that. Now, this is what we have to prove. This is the one that we have to prove. Yeah. So now, if we rearrange these terms here in the sum, can we not just do something like this? Is there something wrong if I do that? Just rearranging them. Is there something wrong if I do that? No,
No,
nothing
miss.
wrong, right? Now, A minus B. This term, is this divisible by M? Based on the hypothesis, yes, it's divisible
Yes,
by
miss.
M. A minus D, is it divisible by M? Yes, it is. So if these two terms are individually divisible by M, can we not say that the summation of them will be divisible by M as well? Yes?
Yes, miss.
Yes, miss.
Yeah, because think about it. If M divides A minus B, if M can divide A minus B, we can say that A minus B is equal to, let's say, MQ for some integer Q, right? Similarly, we can say that C minus D is equal to MR for some other integer R, all right? We can say that, right? If M divides these numbers, then we can say that. So in that case, what is this? MQ. And what is this? MR. And now if you take M in common, what do you get? Q plus R. Yeah. Now this number, is this divisible by M? Clearly it is. M is here. So obviously this number, since this is M is here as a factor, M can divide this number. So there you go. As simple as that. That is the proof. All right. Yeah. Okay. So these are the two properties that we have here based on the summing up the congruence and finding the product of two congruences. So if you have two congruences like this, then you can sum up the left-hand sides. I mean, two congruences where you're dividing the numbers with the same number. So it's the same numbers. Here, see, in the first congruence, we have m. In the second one as well, mod m. It's the same. So in that case, if A is congruent to B mod m and C is congruent to D mod the same number m, in that case, we can add up the left-hand side, and that number will be congruent to the summation of the right-hand side, B plus D mod m. And also, we can say that the product of the left-hand side, AC, is congruent to the product of the right-hand side, BD mod m. Okay, and there are also special cases which are modifications on these properties, generic cases. So if we can say this based on the congruences between these numbers, what about other pairs? What about other pairs? What if there is some other pair of number? Let's say E is congruent to F mod m. G is congruent to H mod m. All of them mod m, all right? In that case, what can we say? Using the ideas of induction, can we not also say that the summation of all of the left-hand side, that is A plus C plus E plus G, is congruent to the summation of the right-hand side, B plus D plus F plus H mod m? We can say that. So basically what we're saying is that this idea that we have, that if there are two congruences in this format, and in both cases m is the same number, in that case, summing of the left-hand side is congruent to the summation of the right-hand side mod m. So we can extend this property for a range of integers, all right? So for a range of integers, a1 until an, a1, a2, a3, a4, so on until an, and a range of integers b1 until bn, if these sets of integers are pairwise congruent to each other, that is, by that I mean a1 is congruent to b1 mod m, a2 is congruent to b2 mod m, a3 is congruent to b3 mod m, a4 is congruent to b4 mod m, and so on until an, which is congruent to bn mod m. If each of these numbers in these two sets are pairwise congruent to each other with the same mod, in that case, using the first property, this one, the summation property, we can say that the summation of all the A terms is congruent to summation of all the B terms, right? That is, the summation of all the left-hand side is congruent to the summation of all the right-hand side, mod m, okay? Also, based on the second property, which is the property of product of congruence, in that case, we can say that same thing. If all these A's are pairwise congruent to all the B's, in that case, the product of all the A terms is congruent to the product of all the B terms, mod m. If they are individually congruent to each other with the same mod, we can say that, all right? Now, what if all these A's are the same number? It doesn't say anywhere that these are going to be distinct numbers, right? So what if all of these A's are the same numbers? What if all of these B's are the same numbers? In that case, what I mean is A1, A2, A3, A4, all of them are the same numbers. A1 is equal to A2 is equal to B, A3 is equal to A4 is equal to A4, and all of them until an. If the same number, what happens to this second generic case, this special case?
This a to the power n.
Exactly. So a to the power of n is congruent to b to the power of n mod m. Okay. So basically, in other words, for some positive integer k, we can say that a to the power of k is congruent to b to the power of k mod m. So these are the special cases we built on top of these properties, right? So we will use these properties of congruences and the definition of congruence to prove other things. For example, things regarding divisibility, whether a number divides another number, proving that a certain number divides another number. We have done that using induction and techniques of divisibility and all that. But it's also possible to prove something like this using congruence and the properties of congruence, yeah? So we'll do just that, just to show you the application of congruence, how congruence, the idea of congruence, the properties of congruence, they are used to prove some of the things regarding numbers, all right? So 41 divides this number. We have to prove this. And we will prove this using congruence and properties of congruence. Now, we don't know whether 41 divides this number or not. So far, we don't know that. Calculate করে তো দেখা যাবে, obviously, but we don't want to do that. We want to prove the basis of that calculation, basically. We want to go to the very basics and prove it using congruence. So now, the trick to do that, first of all, what you should think about is what is the power of 2 that is closest to 41. Why do I want that? Because here, the number that is going to be divided by 41, here we have a 2 to the power of 20. Obviously, we are not going to calculate what 2 to the power of 20 is. তারপর থেকে -1 subtract করে divide করে দেখব না. All right? That is not something we are going to do. We are going to, again, go to the basics and prove the basis of those operations. যে ওই অপারেশনগুলো build করা হয়েছে কিসের বেসিসে? These operations that you can do, AJ division and all of these things, these were built based on the ideas that we're discussing here in number theory. So we'll use those ideas. Now, first of all, 2 to the power of 20, this, the base is 2, and we want to get to a power of 2. So because of that, because we want to get here, because we want to get to 2 to the power of 20, we will think of a power of 2, which is closest to 41. 2 to the power of 5 is 32. 2 to the power of 6 is 64. Which one is closer to 41? 32, obviously, is closer to 41. So we'll use 2 to the power of 5. Also, you will see that if we use 2 to the power of 5, then from 2 to the power of 5 to 2 to the power of 10, from here to here, getting there is quite easy. You just have to do 2 to the power of 5 whole to the power of 4 or square it twice. If you do that, from 2 to the power of 5, you can get 2 to the power of 20. So we'll start with 2 to the power of 5. And what do I mean by that? Now, we don't know whether 41, we don't know yet whether 41 divides this number or not. And the remainder will be 0 in such a way that the remainder will be 0. We don't know that yet. However, does 41 divide itself? Do we know that? 41 এই নাম্বারটাকে ডিভাইড করে যে রিমাইন্ডার 0 হবে কিনা এটা আমরা এখনো জানি না। But can we say for sure that 41 divides 41? Yes, that is something we can say, that 41 divides itself. So we will use that as well. এই আইডিয়াটা ইউজ করব যে আমরা তো জানি না যে 41 এটাকে ডিভাইড করে কিনা, এটা আমরা প্রুফ করব, বাট আমরা at least এতটুকু তো জানি যে 41 divides itself, right? So if 41 divides itself, in that case, we can say that 41 is congruent to 41 mod 41, right? So basically, here, in order to use the idea of congruence, so far we are using 2 to the power of 5. That is the number, that is the power of 2 that is closest to 41. Now, what is the difference between 2 to the power of 5 and 41? 2 to the power of 5 is 32. 32 or 41 এর মধ্যে difference কতটুকু? 9. All right? So basically, 32 এর সাথে just 9 add করলে we get a number which is divisible by 41, right? So 2 to the power of 5 is equal to 32. If you just add 9 with 32, what do you get? 41. And we know that 41 divides 41, right? So এই জিনিসটাই হচ্ছে কি আমরা utilize করব. So we have 32 here. So we can say that 32 is congruent with -9 mod 41, right? 32 is congruent with -9 mod 41. Why? Because A congruent to B mod M মানে কি? A minus B is divisible by M. So 32 congruent with -9 mod 41 মানে কি? 32 minus -9, that is 32 plus 9 is divisible by 41. 32 plus 9 is 41, and we know that 41 is divisible by 41. So we can claim something like this. So we'll start from there. First, we use 2 to the power of 5, all right? Because that is the closest power of 2 to 41, and also 2 to the power of 5 থেকে 2 to the power of 20 তে যাওয়া অনেক easy. Also, we know that 41 divides itself, so we'll use those ideas to establish something like this, that 2 to the power of 5 is congruent to -9 mod 41. So far, is it clear to everyone?
Yes, miss.
Not just that what we did, it's legitimate. Also, why we are doing this. Why 2 to the power of 5? Why -9? Why mod 41? These things. Any questions?
No, miss.
Okay. So next, what we'll do we'll square both sides, and we get what? 2 to the power of 5 whole square is congruent to minus 9 whole square mod 41. We are allowed to do that. Yeah, remember this special case of the second property of product. A to the power of k is congruent to b to the power of k mod m. So utilizing that, we can say that we can square both sides, and we get what? 2 to the power of 5 whole square is congruent to minus 9 whole square mod 41. Okay, so minus 2 to the power of 5 whole square gives us 2 to the power of 10. All right, we can work with that. Minus 9 whole square gives us 81. We have to somehow change it. 81 কে এখানে রেখে আমাদের কোনো লাভ হচ্ছে না to get here. To get here, we need what? We need 1. Remember, whatever number you have on the left hand side congruent to the right hand side mod 41, what does that mean? Left hand side থেকে right hand side minus করলে that number will be divisible by 41. So left hand side we have 2 to the power of 10. এটা থেকে 2 to the power of 20 তে যাওয়া অনেক সহজ. But right hand side we have 81. 2 to the power of 20 minus 81 or 81 square is divisible by 41. এটা জেনে আমার খুব একটা লাভ হচ্ছে না. So what can we do about this? Now think about 81. Is 81 divisible by 41? No, obviously not. But what can you add to 81 to make it divisible by 41?
1.
If you add 1 to 81, you get 82. And we know that 82 is divisible by 41. It's very clear, all right? Just 41 ke just 2 diye multiply korte hobe, which is a very easy multiplication, very simple, straightforward multiplication. So 82 is divisible by 41. We know that. 82 is divisible by 41. So a 81 number ta jeta, so far we have what? 2 to the power of 5 whole square is congruent to 81 mod 41. Also, 81, we can say the number 81 is congruent to minus 1 mod 41. That's correct, right? Because 81 plus 1, 82 is divisible by 41. So we can say that 81 is congruent to minus 1 mod 41. Remember, again, that if A is congruent to B mod M and B is congruent to C mod M, then A is congruent to C mod M. A equals to 2 to the power of 5 whole square, 2 to the power of 10, that is. A equals 2 to the power of 10 this time is congruent to 81 mod 41. And this number 81, B is equal to 81, is congruent to minus 1 mod 41. Based on this property, what can we say then, guys?
Miss 2 to the power 10 is congruent to minus 1 mod 41.
Exactly. We can use this property and say something like that. That 2 to the power of 10 is congruent to minus 1 mod 41. All right. Now we are finally at a point where we can just simply square both sides and we'll get what we needed to prove. If you square both sides, you get 2 to the power of 20 here, and here you get 1. Right? 2 to the power of 20 is congruent to 1 mod 41. And what does it mean? That 2 to the power of 20 minus 1 is divisible by 41. And that is what we had to prove. All right. So you see, you can prove something like this using the properties of congruences. First, we established the definition of congruence. Then we talked about the properties of congruence and how each of these properties make sense. And finally, some modifications on these properties. And these can be used in order to prove things about divisibility. All right. So yeah, any questions regarding this proof?
No, miss.
Okay. So এরকম যে কোনো কিছু থাকলে মানে যদি congruence দিয়ে proof করতেই হয়, in that case, think about at every step what did we do. So 41 divides this number. এই জিনিসটা যদি proof করতে হয় congruence দিয়ে চিন্তা করলে, you have to think about if you don't know whether 41 does divide this number, then at least you know that the number divides itself. 41 divides itself. So use just that. Start from there. 41 divides itself. এতটুকু তো জানি. All right. So start from there. And somehow right hand side যেটা আছে, the number which we have to divide, ওই নাম্বারটার সাথে similar কোন একটা number, that is 2 to the power of 20 আছে এখানে. That's why we brought 2 to the power of 5 here. So 2 to the power of 5 এর সাথে 41 এর একটা association establish করার চেষ্টা করব, which we did here using congruence. And from there we'll go using the properties of congruence. All right. Okay. Next we'll try to find a remainder when a certain number is divided by another number. So divisibility related to এই ধরনের problem গুলো হচ্ছে কি mostly we try to solve, proving that a number is divisible by another number, and if the remainder for that division is not zero, then find the remainder. That's the other kind of problem that we do, that find a remainder when a number is divided by another number. All right, so here, for example, we have the summation of all the factorials from 1 until 100. And that summation, if it's divided by 12, what is the remainder? That is what we have to find out. We will prove this again using congruence and properties of congruence and the ideas of divisibility. Now, 1 factorial is 1, which is not divisible by 12. That is, the remainder of that division will not be 0. Same goes for 2 factorial, same goes for 3 factorial. However, what is 4 factorial? 4 factorial is 4 multiplied by 3 multiplied by 2, which is 24. All right? And 24, is it divisible by 12? Is 24 divisible by 12, guys? What will be the remainder when 24 is divided by 12? 0. So if you divide 24 by 12 and the remainder is 0, can we not say that 24 is congruent to 0 mod 12?
Yes, miss.
Because 24 minus 0, 24 is divisible by 12. So on that note, basically 4 factorial is congruent to 0 mod 12. Now, what is 5 factorial? 5 factorial is 5 multiplied with 4 factorial. If 4 factorial is divisible by 12, 5 factorial should also be divisible by 12, right? Because 5 factorial is what? 5 multiplied with 4 factorial. 4 factorial to okhane ache, and we know that 4 factorial is divisible by 12. So obviously 5 factorial will also be divisible by 12. What about 6 factorial? 6 factorial is 6 multiplied by 5 multiplied by 4 factorial. So again, 4 factorial is there as a factor. And 4 factorial is divisible by 12. So we can say that 6 factorial is also divisible by 12. Right? Does it make sense, guys?
Yes, miss.
What can you say about the rest of the numbers then after 6 factorial?
They're all divisible by 12.
Exactly, they're all divisible by 12 because all of the rest of the factorials will have 4 factorial somewhere there in the factors, all right? And because of that, we can say that the rest of the factorials, all of them are divisible by 12. So for all n greater than equal to 4, or for all n's greater than or equal to 4, we can say that n factorial is congruent to 0 mod 12. Okay, so we can say that. Now, so far we have these, that they're congruent to 0 mod 12 and all that. Now, what about 1, 2, 3? এই তিনটার জন্য কি হবে? Now, we know that 1 factorial is not divisible by 12 such that the remainder is 0. We know that that's not true. However, can we not say something like this? We have this property is congruent to a mod m. We can say that 1 factorial is congruent to 1 factorial mod 12. Based on this property, can we not say that 1 factorial is congruent to 1 factorial mod m? Dono side we have the same number. So 1 factorial is congruent to 1 mod m, basically. So similarly, same goes for 2 factorial. We can say that for 2 factorial as well based on this property. 2 factorial is congruent to 2 factorial mod 12. 2 factorial is 2. So basically 2 factorial is congruent to 2 mod m. Similarly, what can we say about 3 factorial, guys?
3 factorial is congruent to 3 factorial mod 12.
That is 3 factorial is congruent to 6 mod 12, right?
Yes, miss.
Okay. Remember this now. If a set of numbers is pairwise congruent to a set of numbers, then the summation of all the numbers on the left hand side is congruent to the summation of all the numbers on the right hand side mod m, right? Yeah. So here we have all these numbers: 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, 6 factorial, so on until 100 factorial. 1 factorial, where 1 factorial is congruent to 1 mod 12, 2 factorial is congruent to 2 mod 12, 3 factorial is congruent to 3 mod 12, 4 factorial is congruent to 0 mod 12, and 5 factorial, 6 factorial, all of the others, starting from 4 until 100, all of the others are congruent to 0 mod 12, right? All of them have the same mod. So again, here, remember, if all of these A's are congruent to each of these B's pairwise individually with the same mod, we can say that the summation of all the A's is congruent to the summation of all the B's mod n. So using that property, can we not say that the summation of all the left hand side, which is 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus 5 factorial plus 6 factorial, so on, until plus 100 factorial is congruent to the right hand side, which is 1 plus 2 plus 6 plus 0 plus 0 plus 0, and so on until the 100th zero, mod 12. Can we not say that? That basically the summation of all these factorials, which is the summation of the left hand side of all the congruences, is congruent to the summation of the right hand side, which is 1 for 1 factorial, 2 for 2 factorial, 6 for 3 factorial, and for the rest of them, it's 0, mod 12. Can we not say this?
Yes, miss.
Okay. So in that case, for the rest of them, it's 0. The only numbers here are what we get from 1, 2, and 3 factorials. All right. So 1 plus 2 plus 6. So we have what? 9 mod 12, basically. All right. So the summation of the left-hand side, which is the summation of all the factorials, is congruent to the summation of the right-hand side, which is 1 plus 2 plus 6 plus 0, all the zeros next, mod 12. So from there, we get 9 mod 12. All right. So this summation of all the factorials is congruent to 9 mod 12. Now, if it's congruent to 9 mod 12, remember the definition of congruence. In a number, when A is congruent to B mod M, what does it mean? M can divide A minus B. In this case, our A is the summation of all the factorials. Congruent to B, our B is 9. Mod M, our M is 12. So in that case, we can say that the summation of all the factorials, A is equal to the summation of all the factorials, minus 9 is divisible by 12. Can we not?
Yes, miss.
Okay.
Yes, miss.
All right. So if the factorial summation minus n is divisible by 12, then let's go back to the very basic of divisibility. If A divides B, what does it mean? B is equal to AC for some integer C. If A can divide B such that the remainder is 0, B is equal to AC for some integer C. So here what do we have? 12 divides the number, which is the factorial, the summation of all the factorials, minus 9. 12 divides the factorial sum minus 9. So in that case, we can say that the factorial, the sum of all the factorials, minus 9 is equal to 12 multiplied with some integer q. So this number minus 9 is divisible by 12. That is what we can say from this congruence, right? That this number, the summation minus 9 is divisible by 12. Abar etake also based on the definition of divisibility, we can say that this summation minus 9 is equal to 12 multiplied with q for some integer q, if it is indeed divisible by 12. All right. So take 9 to the other side. What do you get? The summation of all the factorial is equal to 12q plus 9, right? For some integer q. So remember now the division algorithm. A is equal to QD plus R. Here, our QD is 12Q. That is, the divisor is 12. We know that the divisor is 12. And Q, the quotient, is that integer Q that we're using. A is the summation of all the factorials. And we have plus R. So what is the remainder then? Based on the division algorithm, our remainder in that case is 9. Exactly. So there you go. You don't even have to go that far. You don't even have to go that far. If this number is congruent to 9 mod 12, what does it mean? A number theke 9 baad dile, that number will be divisible by 12. A number theke 9 deduct korte hobe mane ki? In order to make it divisible by 12, you have to deduct 9 from this number. What does it mean? It means that
9 is the remainder.
Exactly. If you divide this number by 12, 9 will be the remainder. Only because of that reason, you have to subtract 9 from here to make it divisible by 12. That is what it means. So from there, we can say that the remainder from this division is 9. And we got there just by using congruence. Okay. Is it clear, this process of using congruence to find a remainder? Is it clear, guys?
Yes, miss.
Okay, so that's the application of congruence basically. So congruence can be used to solve problems regarding divisibility and such. So that is the use of congruence in number theory. Many other um, things regarding anything related to divisibility and product can be somehow proved using congruence basically, all right? So yeah, and next we'll move into primes, right? So this is again something that you've uh, learned about all your life. We know what prime numbers are. We know the properties of prime numbers and everything. But what is the basis of those theorems regarding prime numbers? All right. What is the basis of those theorems? That is what we'll discuss in number theory. All right. In number theory, remember again that we go to the very basics. So far, all the operations that we have been familiar with. What is the basis of those operations? So, what proof do we have that these theorems or these operations, the theorem that these operations depend on, what is the proof that they hold? All right, we discuss these things in number theory. So primes, yeah. What is a prime number? First of all, can anyone define what a prime number is to me?
Prime number is only divisible by 1 and itself.
Exactly. Any integer that can be divisible only by 1 and itself is a prime number. So basically, for any positive integer p greater than 1, we can say that p is a prime number only if it's divisible only and only by 1 and itself. All right. So in that case, what is the opposite of that? The opposite is a composite number. The opposite is a composite number. We call it a composite number, the opposite of it. That is, any number that is not a prime is a composite. Any number that is not a prime is a composite, obviously. And what is the definition of a composite? A composite is such a number that can be divisible by integers other than 1 and itself. All right. So basically, if some integer n, if you say that the integer n greater than 1, if you say that this is a composite, if n is a composite, you are claiming that there's some other integer a which is greater than 1 and less than n. That is some other integer a, some integer other than 1 and n itself, which can divide n, and such that n is divisible by that integer. Okay, that is what you're claiming when you're saying that some number is composite. Okay, so primes and composite, these are some of the examples of the first couple of primes in the number line. So primes and composites. So when we talk about primes and composites, the first theorem that comes to mind is about prime factorization. Okay, so the proof of prime factorization will do that. First of all, what is the prime factorization theorem? The prime factorization theorem claims that for every positive integer greater than 1, we can say that the integer is either going to be a prime or a product of 2 or more primes. That is, it's a prime, or if it's a composite, then the composite can be expressed as a product of 2 or more primes. All right. These are some of the examples of what the theorem goes to say. All right. For example, for the integer 3, we know that 3 is a prime. So the theorem agrees with this example, or this example agrees with this theorem. And for example, let's talk about a composite. 8 is a composite. We know that 8 is a composite. 8 is not a prime number. However, 8 can be expressed as the product of 2 and 2 and 2. 2 multiplied with 2 multiplied by 2 gives us 8. And as you can see, 2 is a prime number. So 8 can actually be expressed as a product of prime numbers. Same goes for 12. 12 is a composite, not a prime number. However, it can be expressed as a product of prime. 15 can also be expressed as a product of prime. So all integers basically are either primes themselves, or if they're not a prime, then they can be expressed as a product of 2 or more primes. All right. So every positive integer greater than 1 is a prime or a product of 2 or more primes. That is what prime factorization, the theorem, claims. All right. So now, to prove this theorem, are these examples enough? These examples should be enough for proving these theorems. Yes, guys? These examples, the examples that we see here, by just looking at this example, we can say that the theorem, that the prime factorization theorem, this theorem 1 is correct. Just by looking at these examples, we can claim that, right?
Yes, ma'am.
We can. So these examples are just the basis of the proof that this theorem 1 Makes sense. The prime factorization theorem makes sense. Is that what you're saying?
This, I don't think so. Like, if you consider 20, then you have to multiply 4 and, no, it's 2 into 2 into 5. Yeah. I'm confused.
Yeah, sure. If you consider 20, yeah, 20 can be expressed as a product of primes as well. But my question to you is that, are these examples substantial enough to
No,
claim
it's not.
that this theorem 1 is correct, that this theorem 1 makes sense for all numbers? Can we say that? AJ, this theorem 1 is proved just because we have these couple of examples.
No, miss. We have to
Will
prove
it be
it.
enough with any number of examples? No. Why? Because the world of numbers is infinite. There are infinite number of numbers there, basically. So if you bring some more four examples, if you bring hundreds of examples, even then it wouldn't be enough. All right. So example, what I'm trying to tell you is that basically example is not the basis of proof. All right. So whenever you're asked to prove something, you have to prove it by logic. So that is what we will do here. We understand that this theorem probably makes sense based on these examples. That is conjecture. That is not a proof. We can say that, okay, maybe this theorem is correct, or maybe this theorem makes sense based on these examples. That is, you cannot think of a single example. You cannot think of a single example for which this theorem does not hold, right? For any example that you come up with, you see that the theorem holds. However, that is still not enough to prove this thing. That is conjecture, all right? In order to prove this thing, we have to use logic. And in order to use logic, that is why we have all these concepts that we have studied so far. We will prove this theorem in this case, for example, using strong induction, which we have already studied. Okay, we'll use strong induction to prove this. Yeah. So, first of all, what is the statement that we are trying to prove? We have to prove that the statement, we have to prove that the statement Pn is true for all positive integers n greater than 1. All right. So basically, we have to prove that n, the integer n, is either a prime or a product of two or more primes for all integers n greater than or equal to 2. That is all integers n greater than 1. Same thing. All right. We'll prove it using strong induction. Now, remember strong induction. Yeah. Okay, remember strong induction. What are the cases when we use strong induction? Whenever we had to prove something where at some part of the proof it utilizes a range of values, Fibonacci sequence, some part of the proof, all right, it utilizes a range of values, that more than one values preceding k. Remember, in case of ordinary induction, in the inductive step, we assume that the statement is true for some one given integer, and from that we have to prove that it's true for the next integer. However, in strong induction, the assumption is a bit stronger than that. The assumption goes to say that the statement is true for a range of values, and based on that assumption, we again have to prove that the statement is true for the next integer right after this range of values in the assumption. So when do we use strong induction? Whenever we have to utilize multiple values preceding k, all right? Preceding the kth position. As you can see in the Fibonacci sequence, since it's recursive, it utilizes multiple values preceding k. Same goes for the next example. Here again, since it was recursive and it was defined based on the previous three values, here again we had to utilize the three values preceding the kth position. So here, it would be very difficult to use induction to prove these things, because in induction, remember, in the inductive step, the assumption is only for just one integer, and based on that, we prove it for the next integer. But in strong induction, we assume that the statement is true for a range of values, all right? So based on that, that's how we proceed. Since there are three here, we prove it for the lowest three values in the basic step. Since there are two here, we prove it for the lowest two values in the basic step, all right? So similarly, think about the theorem here. What do we have to prove? That n is either a prime itself or it's a product of two or more primes. Two or more primes, all right? So that is multiple numbered product হিসেবেও দেখাতে হতে পারে. So whenever you have multiple numbers involved in the proof, strong induction will make it a lot easier for us to prove this, okay? You'll just see that now. When we discuss the proof, you'll see that it would be very difficult to do it using induction, all right? So now, in order to prove this, using strong induction, what is the basic step? For the basic step, first we have to think about the lowest possible value of n for which we have to prove this statement. What is the lowest possible value of n? N is greater than 1, remember. N will always be greater than 1. Remember, in the theorem, it says that n is for every positive integer greater than 1, so n will be greater than 1. So what is the lowest possible value of n, guys?
Two.
Yes, that's correct. The lowest possible value of n is 2. Since n in the theorem says that for every positive integer greater than 1, so we only have to prove it for all integers greater than 1. So the lowest value of n for which we have to prove this statement is 2. And in the basic step, we prove just that the statement is true for the value 2. All right? And that will be enough for the basic step. And then in the inductive step, using strong induction, if you use strong induction, what is our assumption? Our assumption that the statement is true for a range of values starting from 2 until a certain point, and then we have to prove that the statement, based on the assumption, we have to prove that the statement must be true for the next integer as well. Okay, so this next integer, let us use k to represent this next integer. So basically we have to prove that the statement is true for the integer k, where k is greater than or equal to 3. All right, there is k is greater than 2. K greater than or equal to 2 kore to it's redundant. We have already proved it for 2. We know that for 2 the statement is true. All right, p2 is true, obviously, because 2 is a prime. 2 is a prime number, so we know that p2 is true. So we've already proved it for 2 in the basic step. So it's redundant to say that k is greater than or equal to 2. See, in the inductive step, we are trying to prove it for the next integer. So let's assume k is an integer which can be greater than or equal to 3. Any integer greater than or equal to 3. So our assumption, in the assumption, what can we say? We can assume that the statement is true for all integers until before k. Starting from 2 until before k, the statement is true for all these integers. And based on this assumption, we have to prove that the statement must be true for the next integer, which is k. Whatever the value of k is, the statement will be true for all integers until before k. That is, starting from 2 until k minus 1, for all these integers, the statement will be true. Based on that assumption, we have to prove that the statement is true for k, whatever the value of k is. Now, in order to prove that pk is true, think about the possibilities of the number k. What could be the two possibilities for this integer k? K could either be a prime or k could be a composite. Prime or composite ছাড়া অন্য কিছু তো হতে পারে না. It is either a prime. If it is not a prime, then it's a composite. So it can either be a prime or a composite. Right? Guys?
Yes,
Does
ma'am.
it make sense so far? Where
Yes,
we're
ma'am.
heading? Okay. So k can either be a prime or a composite. What is the first possibility? K might be a prime. If k is a prime, does that not agree with our theorem, with our statement, if k is a prime? If k is a prime, we don't have to prove anything basically. That agrees with the statement. All right? N is a prime or a product of 2 or more primes, remember? Okay. So k is a prime, then the statement is true. What is the other possibility? That k is a composite. Now for this one, we have to prove it. That if k is not a prime, in that case, k is a product of 2 or more primes. That is, if k is a composite, in that case, k is a product of 2 or more primes. That is what we have to prove. All right? So the two possibilities, either k is a prime, which makes pk true, or k is a composite. If k is a composite, what does it mean? Composite mane ki? If k is a composite, it means that there is some other integer between 1 and k that is greater than 1, less than k, which can divide the number k, right? Composite mane to etai bole. If k is composite, it means that other than 1 and k itself, there is another integer, at least one other integer other than 1 and itself, which can divide k. Yeah? Let's say that integer is a. If k is a composite, in that case, there is at least one such integer which can divide k, which is greater than 1, less than k, right? That is some integer other than 1 and k. In that case, let us assume that integer is a. That integer which can divide k is a. So if a can divide k, remember again from the basic definition, the way we define divisibility. If a can divide b, then b is equal to ac, the product of a and c, for some integer c. Yes? So similarly here, if we are saying that if k is a composite, then k must be divisible by some other integer, at least one other integer a, all right? And in that case, k is equal to ab for some other integer b. Yeah? So far, does it make sense, guys? Does it make sense so far?
Miss, can you just explain it once more?
What part? jk is equal to ab.
Miss, ওইটার পরে ওইটা বুঝছি।
k is equal to ab হবে এটা বুঝছো?
Yes, miss.
So far আমি এতটুকুই বলছি, মানে এর বেশি তো কিছু বলিনি। যে if k is a composite, k can be expressed as the product of two integers.
Okay.
Until this point, are there any confusions?
No, miss.
All right. So k can be expressed as a product of two integers a and b. All right. So in that case, think about the integers a and b. What can we say about the integers a and b? Will a and b, these integers, be ever greater than k?
No.
They will never be greater than k. তাহলে তো মানে if k is a composite, in that case it's expressing it in terms of product of a and b. মানে the idea of a composite, it violates that idea if a or b, any one of them is greater than k. If a divides k, a must be less than k. A must be some number less than k. If b divides k, b also must be some number less than k. So basically a and b individually, they are less than k. So if they are integers which are less than k, can we not say that a and b falls under this range? A range er moddhe ki a আর b পড়ে না. In the assumption, we assume that the statement is true for all integers until before k. That is until k minus 1. The integers a and b, are they not in this range, guys?
Yes, miss.
Yes, they are. And remember, our assumption is that the statement is true for all integers in this range. All right? If the statement is true for all integers in this range, then the statement must be true for a and b as well, which are in this range. So basically, pa and pb are true. That is, a and b, each of these are either primes themselves or they're products of primes. All right? So if they're primes themselves, then k is equal to ab is what? Product of primes. If a itself is a product of primes, even then k is equal to ab is a product of primes. Same goes for b. So basically, if a and b, for b, these two integers, if the statement is true, then k is equal to ab gives us what? A product of primes. So k is at least is a product of k is basically, if k is a composite, in that case, k is basically a product of at least two primes, ab, or product of more than that number of primes. In case a and b themselves are product of primes. So basically, k, if it's a composite, is a product of primes, two or more primes. It's a product of two or more primes. All right. So pk is true. So far, until here, tell me if it makes sense. The fact that pk is true and how we proved it. How we proved that pk is true. Any questions regarding that? That pk is true.
Miss, can you explain that assumption that 2 is less than equals to j less than k? The previous assumption that we made.
This
Yes.
assumption.
Yes,
This is just the assumption. This is how we prove things using strong induction, don't we? Remember, strong induction আমরা কি করি? মানে how is strong induction different than induction?
There's
The
like a
basic
range
step,
proof করবো।
yeah, no. We don't prove it for a range of values.
I mean,
We prove,
assume.
yeah, maybe in the basic step, as per requirement, we might have to prove it for multiple values in the basic step. For example, for the Fibonacci sequence, we proved it for the lowest 2 values. For the next problem, we proved it for the lowest 3 values. All right. But in the induction step, I'm talking about the induction step. Induction step is strong induction. And what do we do? The assumption is a bit stronger. The assumption allows us to assume that the statement is true for a range of values. That is what we did here, simply. That the statement is true for all the integers in this range, for a range of values. And based on that assumption, we have to prove that the statement must be true for the next integer, which is k. All right. So a assumption basis we build this thing. If this assumption is true, from there we have to show that k, the statement is true for k as well. Now, the statement for k, if k is a prime, it becomes true. If k is a composite, in that case, k can be expressed as a product of two integers, which will be less than k. The moment we can say that a and b are individually less than k, we can say that a is within the range of our assumption. So based on the hypothesis, we are allowed to say that the statement is true for a and b. And if the statement is true for a and b, since k is equal to the product of a and b, we can say that k is the product of primes, right? Now, is that clear, or are you still confused about the assumption part? How we utilize the assumption here?
No, some clear. Thank you.
Is your confusion perhaps regarding PA and PB? Just that based on the assumption, we are assuming that PA and PB are true. But we haven't proved anywhere distinctly, we haven't proved that PA and PB are indeed true.
Lumis, we have said that the A falls under that range, that the assumption we made previously.
Yeah.
So
Yeah.
it's true.
Yeah. That is what I'm asking. Is it clear to all of you? Basically, I'm asking you about the process of strong induction. Jay, do you guys still have confusion regarding this part, where we can assume that the statement is true for a range of values, and we prove it for the next one, and that is enough to prove that the statement is true using strong induction? That part I'm talking about. See here, we have used the assumption, and based on the assumption, we can say that the statement is true for a and b. But is strong induction clear to you at all? That's what I'm asking. So here, when we have proved that the statement is true for k, once we have proved that, what can we say? Based on strong induction, we have proved it. The statement is true for 2. We have also proved that the statement is true for k for some integer, any integer k greater than equal to 3. For all possible values of k greater than equal to 3, we have proved that the statement is true. So combining the basic step and the inductive step, we can say that the statement is true for all integers n greater than 1. Okay. So based on strong induction, we can claim this. So I'm asking because there were still some confusions left in the last session regarding strong induction itself. That all right, that using the assumption, we can say that P and PB are true. But why does it work that way? That we can assume that it's true for a range of values, and just based on that assumption, we can say something like this. That is, are there any confusions left regarding the process of strong induction? Since you have a quiz coming up, I'm asking. Anybody has any confusion regarding this entire process and the process of strong induction? Guys? Nafisa, Arshad, Fahim.
Miss, it is a bit confusing. I'm just figuring it out.
So tell me, what part is confusing? So we can talk about that, all right? Because if you don't tell me, then I cannot extend further on that, all right? So tell me, mane ekhane, for example, kon part ta you're not comfortable with which part? Just tell me, jekhane kon part e hocche ki you're not comfortable. Are you not comfortable with this k is equal to ab or this? What part are you not comfortable with? Tell me that.
Miss, it's not just that about this theorem. Like normally, আপনি যেটা বুঝিয়েছেন miss, ওটা we can understand. But when we see the question, I don't know how to start. Like go to the strong induction process and prove from there. So it gets more difficult when we solve questions. We don't know how to start.
Yeah, that is indeed a problem. So remember, think about the problems that we solved using strong induction. প্রত্যেকটাতে দেখবা there were more than one numbers involved. Fibonacci, it utilized at some point more than one numbers prior to k. Same goes for the problem after the recursive series after Fibonacci. Here as well, you have a situation where you're utilizing multiple numbers. Here, for example, using induction, it would be very difficult to prove this, okay? Because in induction, inductive step, ordinary induction and inductive step, what do we assume? We just assume that the statement is true for some integer k, and from that assumption, we have to prove that the statement must be true for the next integer k plus 1 as well. So it would be very difficult to prove this using prove this using ordinary induction, because here we have to use the assumption for both A and B. But in ordinary induction, we can assume it for only one integer. And from that, we have to prove it for the next integer. But here we have two numbers for which we have to make the assumption. Yeah. So basically, we have to take a range of values. That is all integers before k. For them, we have to assume that the statement is true. But even that is valid. Even that is valid. We are allowed to do something like that because k is some integer greater than or equal to 3. So if you think about the lowest possible value of k, which is 3, in that case, we've already proved that P2 is true. So this range, the assumption holds actually. If you think about it, assumption, it didn't come out of thin air. It actually does make sense, because let's talk about the lowest possible value of k. What is that? 3. For k is equal to 3, in this range, the only value we have is 2. And we've already proved it for 2. We've already proved it for 2. So the assumption holds, okay? And from there, you prove it for k is equal to 3. And we know that 3 is a prime number. So for k is equal to 3, the statement is true. Now move on to the next k. What is that? 4. When you get to k is equal to 4, what are the integers in this range, guys? K is equal to 4 এর জন্য এই assumptionের মধ্যে কোন integer গুলো থাকবে in this range? 2 and 3. 2 we have proved in the basic step. 3 we have proved before k. K is equal to 4 এ যাওয়ার আগে তো we have proved 3, right?
Yes.
So the assumption again holds, and then you prove it for k is equal to 4. If you can prove it for k is equal to 4, then move to the next k. K is equal to 5. When you move to k is equal to 5, assumption range আছে কি 2, 3, 4. But by then you have already proved it for 3 and 4. So the assumption still holds. All right. So remember the staircase example, the staircase scenario. It's the same thing here as well. It's the same idea here. If you get to a certain number k, it means that all the statement must have been true for all the integers prior to k. All right. So yeah, based on that, that is the basis of strong induction. Now, in order to figure out which method to use, কোন জায়গায় induction use করব, কোন জায়গায় strong induction use করব. First of all, if at some point of the proof you see that you have to utilize more than one integers prior to k for the one that you're proving, k বা k plus 1 যেটাই proof করো না কেন, যেটাকেই proof করছো না কেন, ওটার আগে যদি more than one integer লাগে, in that case you use strong induction, because in induction, the inductive step, the assumption allows us to assume just for only one integer. So use strong induction there. All right. If you have to do something like this for complex problems like this, where you have to utilize multiple integers prior to the integer that for which you're proving the statement, in that case use strong induction. Otherwise use just ordinary induction. And now how to use induction and strong induction to in fact prove these things. So for Fibonacci sequence and the likes, for those things, I've already talked about them in the last session, in the sessions regarding induction, that you have to look at how many values prior to k you are utilizing. In Fibonacci sequence, a certain number is derived from the previous two values. That is why in the basic step, we are proving it for the lowest two values, all right? And for the next problem, it utilized the previous three values. So that is why in the basic step, we proved it for the lowest three values. Here, however, we do not need something like that. Here, simply, k is equal to ab, where ab can be any integer less than k. So here, using the assumption is enough here, all right? So basically, in the basic step, proving it for any integer after 2, it doesn't really make any difference, okay? So that's the process of doing it. So yeah, for the problems that are there in the assignment, all right, some of the students have already sent me emails regarding those problems, okay? So I didn't get the chance to sit for a consultation session to give you guys some hints regarding those problems. Obviously, once again, I'm not going to solve the problems in the assignment for you. I might just give you hints. However, if you come to me with problems from problem set 1, 2, in those cases, I can maybe discuss the problems with you. However, you have to give me a list of problems. So for all the students who've sent me emails so far, don't worry. I will schedule consultation sessions with you. If direct email response is not enough, I will schedule a consultation session with you. However, remember that we will not discuss the solution as long as it's an assignment problem. We will only discuss the possible ways or hints regarding how you could possibly solve that problem, all right? So I'll schedule that sometime. All right, let's end the session here for now. Since this is where I ended for the last section, it went on a little bit further for the last section. So let's end it here. And